Hi everyone, my name is Sarai Rankin. I am a sophomore at Morgan State University, currently majoring in physics. This past summer, I worked under Dr. Alexander Samokhlovov in the NIH RISE laboratories to review the electronic and vibronic spectra of porphyrins and related compounds and emerging applications of solid-state synchronous fluorescence spectroscopy. A porphyrin is an organic material compound that carries out the chemical reactions in cells, such as photosynthesis and cellular respiration. It is composed of carbons in a ring, and when a metal ion is added to the center of the ring, it becomes a metalloporphyrin. Now, porphyrins and metalloporphyrins serve a variety of tasks in the human body as they are found throughout all organic material. They are capable of absorbing and emitting light, they are brightly colored, and contain a complicated spectral structure. They can react under light, serve as catalysts for chemical reactions, conduct electricity, and have magnetic properties. Due to their prevalence in the human body, they are used in cancer treatments for photodynamic therapy. By exciting the porphyrin absorbs and redistributes light to photosensitive drugs that go on to oxidize disease cells. However, there is an issue with photodynamic therapy, as it is difficult to pinpoint exactly where the disease cell is using light, so nearby healthy tissue can get damaged in photodynamic therapy. We can solve this problem by studying how we can study porphyrins more effectively, by finding out which wavelengths of light they respond to the best. We can determine how to affect only the porphyrins and not the nearby cells, so we can treat cancer without damaging healthy patients. Currently, we observe porphyrins and excite them by using traditional spectroscopy. Traditional spectroscopy works by recording molecular absorption and emission spectra. In an absorption transition, an electron surrounding a molecule starts at ground state and absorbs light, is therefore excited to a higher molecular state, or a higher molecular orbital called S1 or S2. And then the light and energy is released in the form of fluorescence and heat, which takes it back to ground state. So it moves from S1 back down to S0. There are certain wavelengths at which an electron absorbs light and can become excited. This is called a vibronic band. There are 4 vibronic bands in a typical porphyrin and only 2 in a metalloporphyrin. The wavelength of light where an electron is energized can also be referred to as the Q band. These wavelengths are found between 500 and 600 nanometers, and the lowest wavelength that an electron can respond to is called the Sarai band, which is found at 400 nanometers. Sarai bands tend to excite molecules up to the second excited state. There are a few shortcomings to modern spectroscopy. Due to porphyrins having such a natural bioluminescence, they appear bright and hazy in a spectrometer. And warm temperatures can cause wider lattice vibrations and phonon lines. This is seen in the figure to the right, as in a room temperature lab, a porphyrin is difficult to spot exactly where its Q bands are, just due to how quickly the porphyrin is vibrating. The range is too far to determine where exactly the Q bands are. This specific problem can be solved by lowering the temperature of the sample significantly, and this is the same sample taken in a much colder room, where it's far easier to find the Q bands. However, not all laboratories have access to a way to lower the temperature of the sample. There is a solution to this problem called synchronous fluorescence spectroscopy, which is what I spent my research this summer working on. Now, synchronous fluorescence spectroscopy is used to excite porphyrins and absorb their spectral bands, emission, and spectral range. It eliminates excessive scanning by having a predetermined wavelength set to collect fluorescence. Generally, finding an emission excitation spectra is time-consuming due to the data collection process of a spectrometer, but to combat these shortcomings, the absorption and emission data is collected in one spectrum. The vibronic structures in synchronous fluorescence spectroscopy here can compare traditional spectroscopy to SFS. A traditional spectrometer would work by exciting a molecule here at A1 and then recording its fluorescence at F1, and then going back and exciting at A2 and recording fluorescence at F2 all the way through A9 and F9. This process takes a lot of time and it's not very efficient due to how broad the specters are, so it does not mark exactly what is important. However, synchronous fluorescence spectroscopy scans record everything as a single spectrum by exciting A's 1 through 9 and then recording only F9. And then at the same time, it excites A9 and then records all of the fluorescences. Here is a result by using the synchronous fluorescence spectroscopy scan on perylene, which is a molecule found in the body. Traditional spectroscopy is seen on the top. Trying to locate the Q bands to which a porphyrin might respond is a little difficult looking at this range, as there could be a peak down around 400 nanometers and another one around 480 and another around 440. It's very difficult to spot where the Q bands, where perylene's molecules might actually respond. However, using synchronous fluorescence spectroscopy, we can clearly see that there is a single spike around 400 or around 410 nanometers and a second vibronic band, which is the Sarai band, around 440. Synchronous fluorescence scan shows the most essential information in this excitation and emission spectra, and it is only done significantly faster than traditional spectroscopy. And SFS can be used in a room temperature lab, so it's actually easier for more labs to have access to this type of data. The conclusions we found is that porphyrins have a complicated electronic structure but can be utilized to perform a variety of tasks in modern medicine. The existing methods to study detailed properties of porphyrins and vibronic structures specifically are limited by conventional spectroscopy. However, using SFS, it works efficiently to resolve vibronic structures issues at room temperature. It is of great interest to investigate synchronous fluorescence spectroscopy to reveal fine detail of spectra and porphyrins and related compounds. I'd like to thank the RISE staff and my mentor, Dr. Alexander Samoklevov, and just NIH RISE as a program in general for funding this research. And I hope you all have a wonderful day.